Hopefully it clears out any. All right, so let's get started. Tonight, we're going to continue where we left off last week with decision trees and ensembling. I got a suggestion that I go through an example of a decision tree. Just basically, I figured I'd do it in Excel. So we're going to go through that tonight first, give you guys more of a feel for how a decision tree gets developed through that the algorithm that we went through in Python last week. So, right, just my information. Okay, so that's the first thing we're going to do is going to go through the iris example, iris data. We're going to develop a decision tree for the iris data. You'll see it happens pretty quickly. And we're just going to do it in Excel from scratch. Well, I did it, and I'm just going to show it to you. We'll walk through it. Then we're going to go into boosting. Stuff we did, we started on last week. It's one of the ensembling techniques for decision trees. We're going to talk about add a boost first, and then gradient boosting, and then XGBoost. And then, well, we're not going to talk about LightGBM. I think we're just going to run out of time by then. So everything we do with XGBoost applies to LightGBM. It's just going to be a more accurate and faster model. So, okay, so let's look at this spreadsheet here. Okay, and okay. So this right here, as you can see, is the iris data. It's got 4 columns: sepal length, sepal width, petal width, and what species the iris belongs to. And there are 3 different species, 50 data points on each species. So what we're going to do is we're going to train a versicolor classifier. Not all 3, we'll just do 1. But the same thing would apply. We just would multiply this by 3 with 3 different outputs rather than just 1. So I took that data set and I changed it from, well, it was species before. Now it's just either 0 for everything other than the ones where it is a versicolor iris. And so we're back to 0 if it's the Setosa or Virginica species ends up being a 0, and a 1 if it's a versicolor. All right. So first thing we need to do is start the decision tree. Start figuring out what's our first break. What's our first dividing point? So what we do is for each of the 4 descriptions, we're going to try each row and make a calculation of how good that particular feature is, what that row is, how good it is, to dividing our species up. So what I first did was, okay, so I'm going to use the Gini score to calculate that. So what I did was I sorted by sepal length. And so I have all of the different sepal lengths. I got 4.3, 4.4, 4.5, 0.6, all of them up to 7.9. So I need to try each one of these, figure out which one of these is the best break. So basically, if it's less than 4.3, then it's one species. If it's greater than 4.3, then it's another species, or greater than or equal to. Let's put the equal sign on the greater than. So starting with a 4.3, and I'm saying, okay, is the sepal length greater than 4.3 for this one? Is it, or is it not? Turns out all of them are greater than or equal to 4.3 because it's the smallest one. So what percentage of the time was this, just this SL greater than or equal to 4.3? What percentage of the time did that give us the right answer? So if we go down, take a look. So here it guessed right for a couple of them. But mostly it's wrong because it said everything's a versicolor. But we know only 1/3 of them are versicolor. So therefore, my Gini ended up being a 0.333. So that's not so good. So now I move along to 4.4, the next value. And I say, okay, how many of these are greater than 4.4? So this one is not. It's the only one that's not. All the rest of them are. So then I say, okay, how many of these did I get correct? Okay, this one turned out to be now correct because it's not greater than 4.4. And going down, so that's the only one that changed. I now have a little bit better score here, 0.34. And I kind of have this backwards. It should be, as it goes lower, it's more correct. So this is not really the Gini score, it's more accuracy. But I have it corrected, going forward. So as you can see, this is a very labor intensive process. I'm going to take a lot of columns here to do this. Well, there's a better way in Excel to do this. If I just have the score automatically calculate for 4.3, have it automatically calculate for 4.4, like this, going down rather than creating all these columns going across. That'll take a lot of space. So what I did was on this page, okay, so here's my data. And then, so here's my output. So I did a lot of magic in Excel to come up with Gini scores. So what I first did was, okay, I got a column for versicolor, I got a column for not versicolor. And for my first two columns here, I have this is one comparison, less than or equal to 4.3, and the other one is 4.3. And so now for my Gini, I'm doing a sum if. I'm taking two different sum ifs and adding them together. One is a sum if on whether I got it right, and it is a versicolor. And the other one is if I got it right and it's not a versicolor. So I, taking all those, adding them up, and dividing by 150 to get my Gini score. And I'm going to put this in order. It is already in order, okay, by sepal length. So I can see here, 4.3 is my worst Gini score. Actually, it's not my worst. It does start to get better as I try 4.4. It's a little more accurate, a little bit better. As I go down, increase this number, my Gini score gets a little more accurate. At some point, I'm going to end up with an optimal break. Looks like 0.453 might be it. But no, it actually is going to go lower. Ends up being, the lowest one is 0.33. Okay, and that's breaking on 7.9. So SL is not a very good Gini score because not a very good measure, because the smallest number gives me my worst and my biggest number gives me my best Gini score. If I look at other columns, I've done the same thing for sepal width. We put it in order by sepal width. Okay, let's take a second there. Okay, so okay. This is I can't sort it. Hold on one second here. Okay, here we go. Okay. If I sort it, it messes up my calculations. All right, so we're gonna have to do this without resorting it. So for the sepal width, I come up with the lowest calculation of 0.26. So that tells me that sepal width is a better way of subdividing my data than the sepal length. And also with petal length and petal width, I get also 0.33 is my lowest. So it's better to break on this one, on the sepal width. And where do I break? I break wherever I got the lowest value, 0.26. So that's where sepal width of 3. That's where I get my lowest one. So what I have is, for where it's greater than or equal to 3, I've got, I can say that I can guess that I'm a versicolor, versus if it's less than 2.3. Okay, I got a question. Is 3 the median value in sepal width? No, it's not. These range from, like, let's go back to our original data. We can see by sorting this one. The lowest one is 2. The highest one is 4.4. So 3 just happens to be where we get the best cut between being a versicolor and not being a versicolor. We get the most right if we subdivide it there. Okay, so what we're going to do now is, well, we've just decided what our first break on our data is the sepal width greater than 3, it's versicolor. If it's less than 3, then it's not a versicolor. We can break it down further and see if we have another break that will give us even more accuracy. So take half the data, or the data that's above 3 and the data that's below 3, and do 2 more decision trees. So that's what I have on the next 2. Here's the data where the the sepal width is less than 3. We only have 59 rows, or actually 60 minus 3, or 57 rows. Now Gini B, I have the rest of them. I have where the sepal width is greater than or equal to 3. Here I've got more rows, 96 minus 3, so 93. So that adds up to 150. So now I repeat the process. I start with the sepal length, and For every sepal length, I calculate what my Gini score is. So this is what they are. And then what's my minimum Gini score? Minimum Gini score is 0.11. And if I look for where this is 0.113, it's here. So that means that 6.3 would be my breaking point. Above 6.3 is one, below 6.3 is the other. But if we look further, we see that pedal width actually is our lowest Gini score, 0.03. So where is that value? Where is that break? If we look for 0.03, it's in here somewhere. Here it is. So if we look for 1.7, 1.7 is our pedal width, where above it is one value, below it is the other. Okay, so that now we can break our data into two more decisions, and that will be AA and AB. But we'll get that in a second. We still need to do B, Gini B, which is the other data. It was the sepal width greater than 3, going down the other side of the tree. If we look here, we ended up with a minimum Gini for all four being the same thing, and it happens to be the smallest values for each one. Nothing is smaller. So this doesn't cut it in the middle. So one side of the tree will have no rows, and the other side of the tree will have all the rows. So that ends up being a terminal tree, a terminal leaf, our B side. However, our A side, we saw we could break it up further. So let's do that. Okay, so again, so I got Gini AA here is going to be all the pedal widths greater than 1.7. See, there's not too many. And our Gini BB will be all the pedal widths that are less than 1.7. Looks like I included 1.7 in that, but that's fine. So let's calculate our scores again. Our Gini scores with, for this data set. And it looks like our Gini score is all zeros, which means I have a perfect split at this point. As you can see, everything I split here, everything I came out with was not a versicolor. I'm sorry, yeah, was not a versicolor. Not versicolor is 1, versicolor is 0. So basically everything with pedal width 1.7 or above is not a versicolor. And Gini AB, get that one. This one, for these values, if I look at the Gini scores, minimum Gini score, 0.026, these two are equal. But if we take a look, that 0.026 is the smallest value. So this would be another terminal leaf. We're almost 100% for this. We're missing a few with this particular split. Okay, so we have two splits, and I summarized those splits here. Let me unhide these columns. Okay, so the first split was sepal width greater than or equal to 3. We have a no, and we have a yes. The yes ended up being a terminal tree, a terminal leaf, and that was not a versicolor. If it was no, that was more apt to be a versicolor, but we could split it again for pedal width greater than or equal to 1.7. If it was no, it was a versicolor. If it was yes, it was not versicolor. So this is a very short tree, but this is the best tree we could come up with. So what I did here is, here's the actual species. Here's the prediction that my decision tree came up with. If you can see, it's if Versicolor is greater than 3, it's a 0. Or if Versicolor is less than 1.7, so 1, otherwise 0. So I coded this simple decision tree into this prediction. As you can see, I got it right for a lot of it. A lot of zeros. So this is my loss function over here. You know, 0, it's absolute of the difference. So it's 0 when it's correct, 1 when it's incorrect. Down here, I've got a bunch of 1s because I guessed incorrectly. It's not a perfect decision tree by any means. At 86% accuracy. So with a decision tree, very basic decision tree, 86% accuracy. That's pretty cool how this just kind of came out of this algorithm. It's not perfect because we don't really have a perfect model. We don't have perfect data. You never really do. This is somewhat random data, so you'll never get a perfect model. But anyway, so that's, to me, this was extremely exciting to go through this. And I've included and shared this this for you here in the go ahead and share it. Put this on the copy, put it in the chat. Okay. All right. Okay. So you guys can go through this yourself. You might want to try it for one of the other classifications. All right, so let's talk about gradient boosting now. All right, well, okay, not gradient boosting, but just boosting, because the first one we're going to do is add a boost. All right, so you guys remember what bagging was? Bagging and the random forest are where we limited our data set to, we took out some observations and just trained it on a subset of the data set for bagging, or a subset of the features for random forest. So we're not going to do that. We're going to use all of the data, but we're going to create a bunch of weak learners and train on those weak learners. I'm going to start with, very, very simple, like one cut of the data on our, like if we're using decision tree as our weak learner, then we're going to create one node, not the whole decision tree, but just one node of the decision tree. And then the incorrect values, the incorrectly predicted data sets, that those rows, we're going to boost the value of those. We're going to boost how much we're going to train, how much we're going to consider those particular rows. The ones we got right, okay, we got right. So we don't care so much about them. We do care more about the ones we missed, and we're going to try to train on those. So basically, we're going to train many weak learners. And usually what you use for your weak learners is a decision tree, and you create what's called a decision stump, which is just one break of your data, one split. So, and you figure out what mistakes you make, and you create another learner. You boost those mistakes, make them more valuable, and then create another weak learner, and you consider those more in the weak learner, and you should have progressively more accurate learners, and then you combine them. So this is kind of a depiction of how AdaBoost works. So here's your data. You create one quick split on the data, the best one you can do. So and it got 3 wrong, because what I'm trying to do is split between the minuses and the pluses. So it got 3 of the pluses over in the minus side. So what I do is I boost those, make them more prominent in the next decision tree, and train again. And I ended up with a different split. Now on this one, I got a few wrong. Got the minuses on the wrong side, so I make those bigger and train again, come up with another split, and so this time it ended up with this being the split, the basic split. And then what I do is I combine all these 3 together, and I can end up splitting everything equally, correctly, if I do it correctly. Here's the math behind it. I'm not going to go through this, but this is, they come up with this normalizing factor, alpha, that is a measure, is how much you boost your incorrect values, your incorrect rows. So that's how they do this. They come up with an exponent, and it's complex how they do this, but this is the basic methodology. And this is as much as I'm going to do for AdaBoost, because it's not very popular. Not a lot of people use it. So, we're going to move on to gradient boosting, which I'm sure you guys have heard this many, many times. Much more popular. So there's basic gradient boosting, and then you have a few variants that are on top of that, XGBoost and Light GBM, which XGBoost really isn't that much different than gradient boosting. It's they just add a lot more bells and whistles to it. Other than that, it's exactly the same methodology that I'm going to explain here. So I'm going to go through this a few times. The basic way that gradient boosting works is you start again with a weak learner, like a decision tree that's just one split. You calculate the error residual, how far off this was. As you can see, this harkens back to the AdaBoost. It's very similar. Sounds very similar. You calculate the residual, and then you train another weak learner on as if that error residual was your original data. And you understand, everybody understands what residual is. It's the difference between actual and your predicted. That's it, just the difference. So you have this residual. You create another weak learner on that residual, on that difference, and keep doing that. And your final model is the sum of all of those weak learners. Each time that you calculate your residual, it should go down. Your residual should decrease. So because your model keeps on getting closer and closer to what your data is, what your what your function is. So to show the math, to everything I just said, let's put it in mathematical terms. You have your predictions for your function, and then you calculate a loss, which is what your residual is going to be. And then we calculate a mean squared error. And what we're doing by training another weak learner on that loss is we're finding out the partial derivative with respect to the your predictions. So, and then we have this alpha in here to modulate how much we're considering these additional weak learners. So we keep doing that. If we take the derivative of this, we'll just take the 2 on the outside. Ends up being just the difference. Okay, we got a question here. Explain the fourth expression again. Okay, how do we get this expression? How does it relate to gradient descent? Well, gradient descent is you're modifying your prediction based upon how much the loss, which direction the loss will go, if to make it smaller, which is the partial derivative. So that's that's the key to this. So it's good if you want that explained more. This is the basic tenet of gradient descent. Yes, that's a good point. You subtract. That's a good point. I don't know why it is adding. Yeah, I don't know. That is a good point. Loss should get smaller as you get closer. I don't know the answer. That's a good question. Okay, so so another way of talking about this, another way of describing the steps for the gradient descent. We kind of talked about this once, but here's another way way to describe it. So we start with a basic prediction, and a mean is a very good, well, not very good, but it's a good place to start for your prediction. Just a mean of your y. So, and then you figure out what the errors are from that, of each observation from the mean. And this, the mean is what your latest prediction is. So you figure out how far off your mean is from your observations. So that becomes your residual. So then you come up with a split on the errors. And that is your first decision tree, your first model. And whatever that splits your errors perfectly, or the closest, that ends up being, quote, your latest prediction. And your final prediction will be that plus your previous prediction. Okay, so you have your latest prediction, you calculate your errors again. And then that becomes now your latest prediction. And you keep on going until you get to a minimum of your error. And then your final model is the weighted mean of all weighted mean of all your classifiers. Weighted sum divided by total number of them. Okay, so this is a pictorial of how the gradient boosting works. Let's say this is your function. Between 0 and 10, you have kind of a randomized 10, or maybe 12. Between 10 and 20, you have like a 22. Between 20 and 30, your output's like around 0. Between 30 and 40, it's around 30. 40 and 50, okay. So your first split on the data, if you're to come up with a decision tree on this, may look like this, where if you're less than 30, you're 12. If you're greater than 30, you're 21. That's a pretty rough estimate of what your function is. But that's, so decision tree starts out not being very accurate. So then you calculate what your residual is. You take the difference between all of these and your guess, your prediction, and this is what you get for your residual. Now you break this, you do a decision tree on this one. And the decision tree on this one ended up being breaking way out here on 40. Then add those two together, and now this is what your function looks like. It's going to be a little bit more accurate. Here's your residuals. Here are your differences. It's a little bit less than it was. You can see that these are a little closer to 0. Your residuals should go towards 0. So do it again, and you end up splitting a little bit higher now the next time. And residuals ended up being a little bit closer to 0. Do another split. This time it decided to split down here. Right, see, my residuals are getting closer and closer to 0. And if I do this, and that was iteration 4, if I do this 29 times, this is what my function ends up looking like. My mouse just died, okay. And my residuals are all around 0. If I keep going, they will end up being even closer to 0. So after a sufficient number of iterations, I'm getting closer and closer to my function. Okay, so now let's look at gradient boosting, a Python version of it. And we're going to do this from scratch. We're not just going to plug in the model and say fit and what's the output. We're going to actually look at how inside gradient boost and how it works. Okay, so pull that up. Let's see here. 1 second. Gradient boost. Here we go. Okay, so here are the libraries we need. Notice we're not pulling in the gradient boost library, so run that. Okay, so we're doing a decision tree as the weak learner. So here's a function that defines a decision tree. Not much unlike the decision tree we went through before. So I'm not going to go into the details here, but we're going to use this. Okay, so first thing is to create our data set. So our data set, creating a data frame, and we're putting in random values, 10, 10, let me see, 10 to 15, or 20 to 25, 0, and we're putting all of these functions together. So we're actually creating a function ourselves rather than reading in data. And if I plot the data, it ends up looking like this. So that's what we're going to learn, is this data. Okay, so, all right, so we're initializing our input as X and our target is Y. So just setting YI and XI. And then our error, we're setting it to 0, but we're going to calculate it in a second. Number of rows for this is just the length of the YI, which is 50 rows. And our initial prediction is just all zeros. Okay, then we're going to iterate 30 times. And I'm instantiating my tree as being a decision tree with Xi and Yi, and it's going to find a split. Basically, that's the first thing it does, is find the first split. And R is okay. So we have this. Where did it split? It's a single split. So where did it split? We got a left side and a right side. So we're creating a left index and a right index based on where exactly it's split. And then we're going to create a prediction of left and of right based on what we just split. So we're creating a function here. Function is PREDI, and we're going to take the mean of the left side and the mean of the right side and repeat it the number of times that will end up making this function. So on one side we have the low value and the other side we have the high value. And now we're going to change that a little bit so that we can add it to our old prediction. Our old prediction was just all zeros. We're adding this to come up with our new prediction. We're adding the two predictions together. Then we're going to calculate what our residual is, our error Y, which is our actual, minus our prediction. And our predicted Y, we're saying is the residual. Okay, so then we're going to plot our residuals, plot our prediction and plot our residuals, plot our original function on a couple of graphs. And as we go along, as we iterate through this, it will it'll add to this. So the first time, this is what we got for our prediction. Second time, we got a little bit closer. So this is basically the charts I showed you before. And it's getting closer and closer as we go along. So this actually works. I mean, with a basic one step decision tree, we just ran it many times and just continued to add together all of these splits, and it ended up with a function that really closely shows closely like our data. So it's pretty amazing. And it's really not that complicated, not that much code to do this. All right. So, all right. So what are the different parameters with the gradient boosting, scikit-learn function? If you're going to use that, it's got, it's much more complex than our simple one. I say that, but there's not really much more here than what we calculated, or what we used to calculate ours. Something like a minimum sample, split, and leaf. Those are properties of the decision tree. We didn't incorporate those on our decision tree, but we easily could. We did on our last one when we created this ourselves the last time. So weight fraction. So how much of the leaf goes to one side or the other? Is if it's splitting, to whether we want to split again or whether this becomes a terminal leaf. How deep do we want our basic terminal, our basic tree, our weak learner to go? What's the maximum number of nodes for our weak learner, and maximum number of features? I don't know how, or maybe, yeah, this is if we're going to cut down our tree and only use some features, not all of the features, our weak learner. So different other parameters that affect the boosting part of this, not necessarily the tree. Learning rate. So we just added them together. You know, there's an alpha in there. So instead of using a 1, we could add only a part of the next weak learner rather than the full weak learner. So that would be learning rate. And estimators would be, okay, how many times do we iterate through this before we're done? Subsample, not sure what that one is. Loss, there's different types of loss functions that we could use. We use just the difference in ours. But there's other types of loss functions. You know, there's the difference squared. There's the absolute value of the difference. So there's different ways of calculating that. Init, not sure what that one is. Random state, you know, that's so if you want this to be repeatable, you can set the state to be a specific number, and then each time you run it, you'll get the same results, rather than it starting at a new random random state. Verbose is whether you want the function to spit out information as it's running. Default, I believe, is verbose equals off. So it's silent. It runs quietly, doesn't tell you much about what's going on inside before it's done, and that's part of the fitting. And then pre-sort, not sure what this is. Probably has to do with how the data is sorted before it runs. Maybe it goes faster if it's sorted a particular way. Okay, so that's it for gradient boosting. Pay attention to the time. All right. So the next thing we're going to look at is a variant on gradient boosting, which is XGBoost. So it's like a boost on a booster. You know, it just has a lot more bells and whistles. So the advantages that it has is it's got regularization in it, L2 and L1 regularization to help with overfitting. It has the ability to run to take advantage of parallel processing. So if you have more than one processor, you know, quad processor, then this will take advantage of that, whereas the boost algorithm doesn't. There's other optimizations and evaluations that you can do. There's it's more complex in that area. If your data is missing, like it has you know, nulls in it, then the XGBoost can handle that. The boost algorithm, gradient boosting, doesn't handle it. This one allows you to do tree pruning. So it's, you know, if your tree gets too big, then there's a way of cutting down the size of the tree to get a more accurate answer, or less overfitting. And this gives you some cross-validation options, whereas XGBoost, just straight, you'd have to implement the cross-validation yourself. Okay, so some of the parameters for XGBoost. A lot of these are similar to the boost, the gradient boost, but some additional ones. So you can define what type of simple your weak learner you're going to work with. It can be a tree or linear. So you set it to either this one or this one. And usually people use the tree rather than using a linear, linear algorithm, linear model. When it's silent, yes or no, this is similar to verbose, but the opposite. Okay, here you can set it to the number of threads that you want to use, or it can just go, do the default, which would mean all of them, as many as it can. So some parameters that are specific to the boosting. ETA, learning rate, that's analogous to the learning rate in gradient boosting. Minimum child weight, not sure what this is, but it has to do with how deep your weak learner is going to get. Max depth, how far you want your weak learners to go. Max leaf nodes, how many leaf nodes do you want for maximum for your weak learners. Gamma, not sure what this one is. Delta step, this is another part, like this part of the learning rate. So subsample, so if we're going to do bagging with our weak learners, then here's where you would specify that. Number of column samples by tree, I'm not familiar with that one. Lambda and alpha, these are the ratios of L2 regularization, using the ridge method, or L1 regularization, which is lasso, or that's alpha would be that one. Scale POS weight. So yeah, and I'm not sure what this one is either. Okay, so some other parameters for the learning part of this. So different objective or loss functions, these are the different optimizations you can do with this. It either can be the linear, binary, softmax, or soft probability. These have to do with if it's a classifier. You can put these functions on the output if you want. Linear is all that we were doing. Okay, so different evaluations for the metrics, the loss functions like RMSE, and seed would be your random value. So that's analogous. So it's just a little different implementation of the gradient boost, but more possibilities with this. Okay, so what we're going to do is go through an example of XGBoost. And it's not that fast on my machine, so I'm not actually going to run everything, but we will step through it. I have run it already. So we can just look at what the output is. Actually, except for this part. Part of this one, this one, it splits the data preparation, the EDA, out from the actual model building. It's two different Python files, two different notebooks. So this part we can actually run through. So let's just take a look how this generally works. So pull in the libraries. Okay, I'm pulling in this data. So I've got a training data set and a test data set. Okay, it's taking a minute for my libraries to load. Okay, so now load training and data set. It's not overly huge, so it doesn't take too long. So it's 87,000 rows for the training, and the test is 37,000. And taking a look at the training types, you can see what they are. Okay. Okay, so first thing is it combines the data, combines it into one table, taking out the index, and ends up with 27 with 124,000. So we're seeing how many missing records, missing values we have in our training and test data. This is all standard EDA that you should get very, very, very used to. Standard data science stuff. I'm going through all of the models, but this is all extremely important. So looking at how many null values we got in these, which we have quite a bit. So this puts it in order. These null values this is how many different values do we have in each of these, each of the features, and puts it in order. So some of the features have many, actually, okay, we're going through each feature and looking at how many of each of the different values. The first one is salary account. Actually, no, the first one is gender, and there's 71,000 male and 53,000 female. For salary account, this is where they put their accounts, put their money. Okay, whether they're mobile verified, shows how many are each of those. Just keeping going down, it's actually what they did. They only did this for certain variables, not all of them. The ones that are object variables, the ones that are classifications versus numerical. Okay, so how do we handle, okay, so looking at each variable, so it's, okay, we're dropping city because too many unique, so it really doesn't make a difference to the model if you have too many unique values. Now switching, converting the date of birth to age. So here's what our date of birth is. Date of birth values are a few of them, just the first 5, and then use this 115 minus the last 2 pieces of the string, converting it to integer, come up with the age, which was the age as of when this was written, not necessarily now. So, and adding age to data, okay, to our input, and then we're dropping the date of birth. Okay, and EMI loan submitted is doing a box plot on that. See what it looks like. Majority are missing, so creating another variable for when they're missing. That's one way of handling missing data, is creating another column that is a 1 whenever you're missing the data. That way you're not losing information, you're not, if you set it to 0, you're still continuing keeping the data, keeping the information. Actually, they just dropped that column. All they want to know is whether they have it or not. They found that was the most useful. Okay, so how many different employee names, and they're dropping that. The employer name is, you're not going to get much information out of that. Not enough people all work at the same employer to really get much information out of that. So then existing EMI, creating a box plot. See what they're going to do with that. They're giving an idea of what it's like. Okay, so I guess we're missing a bunch of values. So wherever it's blank, put in zeros. There's only 111 missing, so that's okay. Okay, the interest rate. Here they're adding, a 1, so this is how they're imputing data based on missing data, and then dropping the interest rate. Okay, so then lead creation date. So what they're saying is, okay, generally lead creation is not going to have add much value, so we're just going to drop it. Okay, so looks like they're just filling in the median wherever there's data missing from loan amount applied. There's only 111 missing, so they're just adding the median. Okay, so for loan amount and tenure, there's a lot missing, so they're going to add a column for whenever it's missing, and then drop the old values. Okay, don't need logged in. Don't need salary account. Okay, so here it's adding a column for whether it's present or not. So some good techniques here for dealing with missing data. Okay, so source. So it's for where it was missing, they changed it to others. Okay, so what the final data looks like is this. Okay, so they still have nulls in dispersed. Okay, so now doing the fit transform to convert the labels to separate columns, one hot encoding. So that's what this is doing. And looks like it's going to take a minute. Okay, then we're going to break our data back up into training and test. And then drop this, let's see, drop some columns, source and dispersed from the test. Oh, test, that must be the output, the dispersed, dropping source from everything. So source was, when we combined these two together, we added a column to say whether it was training or test, so that we could remember that. So that at this point we could split it apart. And then we write the output to some data files, some CSVs for us to read in on our other file, our other program. Okay, so we're done with this. Close it. Let's go ahead and save it. It's complaining. Okay, so now let's go into, so see, we've got this test and train modified, which were updated just seconds ago. So let's go into the XGBoost modeling. All right. Okay, so first thing is load up the libraries. Okay, that's still running. Okay, got some mornings. Okay, some information. So we're loading the data. Okay, and then looking at the shape. Okay. Okay, dispersed is a bunch of, dispersed is what we're trying to learn, whether a loan was dispersed or not. And zero, it was not dispersed 85,000 times. It was dispersed one time. I'm sorry, 1,273 times. Okay, so what they do here is they create a function for cross-validation, which is quite nice. They call it model fit. The algorithm is what's passed in, which will be the XGBoost, the training data, the test data, what are the predictors, whether by default cross-validation on the training, number of, by default, what are the folds for the cross-validation, and then early stopping rounds. That's one of the parameters in this. I forget where that comes in, but basically they create a matrix and they do the cross validation here. It's xgb.cv. So an xgb that's the library. So it's got its own cross validation function. So we said before that was something added into the XGBoost. So here is the function. That's if we're doing cross validation. Use train CV is passed in. Then we fit, and then we do predictions, and then we do the predict probability, which I don't know if you remember, that gives us the probability of the output rather than the actual 1 or 0, rounded up or rounded down. This gives us the before it's rounded up or rounded down if it's a classification. And then we print reports. What's the accuracy? What's the area under the curve? So it's got a ROC score, ROC AUC score. They have that in here for just between, the training. It's just on the training. AUC score on the training, not necessarily in the test. But here we calculate, okay, what's the result on the tests, or what kind of results do we get? Okay, so that's our function, just defining the function. And so the first thing we do is a basic use for high learning rate. So for predictors are all of the columns in the train, except for the target and the ID columns. So we're just defining our predictors. That's our X. And we define our XGB classifier here, and then we run model fit, passing in that XGB classifier and the training data, the test data, and what are the predictors, the X, the total, all of the X, all of the column names. And this takes a few minutes to run. We'll go ahead and run it, once here, just to show you. Okay, so okay, good. Okay, so then we're defining a few things. Defining a grid search CV. So this is a way that you can, for the classifier, the XGBoost classifier, go through several values of parameters and run it on each one of those. So this is, if you take a look here, we're setting up a definition here, a dictionary for max depth is going from 3 to 12, skipping 2. So like 3, 5, 7, 9. Okay, and then min child weight, we're having it go from 1 to 6, skipping 2. So 1, 3, 5. So we're coming up with a grid here for parameters for max depth and min child weight, some of our, our parameters. And we're creating an estimator and and then we're sending in also a parameter grid with those parameters. So basically what we're doing is we're doing a cross-validation, trying all these different parameters and seeing what it comes up with. See what kind of answer we get. And though that takes quite a while to do, because here we're just running one. If we do this one, it's now doing many different variables, many different training fit. It's doing one for each one of the different parameters that we're sending in. So what I'll do, instead of just waiting for that letting it run and waiting it to finish, we'll just go to the next step, which says, give me the scores. Give me what the final output is. If I run all of the different those different parameters. So as you can see, max depth is going 3, 5, 7, and 9, and min child weight is going 1, 3, 5, and it's doing all combinations of those. So what we're getting for our mean error is here. Our accuracy, I should say, not error. Our highest accuracy ends up being this 0.84133. So when we tried all of these variations, we found which one was the best. 5 and 3. So and this is the functions that we are running here to get this. So gsearch.grid_scores gives us the scores. gsearch1.bestParameters gives us, okay, what was the best out of that? And then what was the best score given those values? So that's what happened when we were in that. So we found what of our best values out of this, best parameters for 2 of them. So now on our next round, we plug in those best parameters and now vary something else. Now we're setting parameter test 2 to be our maximum depth and minimum child weight for several different values. We're trying different things, trying a grid here. This will be 3 by 3, so 9 different times we're running it with different parameters. So if you take a look down here, when we define this, we said max depth equals 5. So we plugged in what our best one was. and min child weight equals 2. Now notice that this min child weight and this min child weight are not the same. I should have plugged in a 3 here, but I didn't. I plugged in a 2 because whenever this was run the last time, it came up with different results. You know, there's a randomization factor coming into play here. So one of the homework assignments is actually run this and plug in these best values and see how it runs. The way I did it, I didn't just take whatever the best was and plug it in. I just ran it as is. Figured I'd leave that up to a homework assignment. Okay, so when I run it with this set of parameters, I end up with several more results. Here's nine different results I got. And it looks like this one's the winner. So yes, max depth 5, min child weight 4. So what I like about this, there's some things I like about it and things I don't like about it. Okay, max depth of 5 is good because that's in the middle between 4 and 6. So I know that if I go higher than or lower than 4 or higher than 6, most likely I'm going to end up with a worse error, you know, worse accuracy. However, min child weight ended up with 4. So maybe 3 might be higher. Maybe 2 might be higher. So really we should run this again, you know, with maybe min child weight of 2, 3, 4, 5, like that, rather than 3, 4, 5, 6, because we might get a better answer with 3. Okay, so then moving on to the next, you find you basically there's like an order of parameters that you would tune as you go through this. So I mean, basically, we're tuning hyperparameters. The next one that they tune is min child weight. So they plug in what we found was the best one, best parameters from before, and now we're varying min child weight. And you can see with those 4 values, we ended up with the best one being 6. This is a little unnerving because 6 gave us a high one, 8 is a little bit lower, 10 a little bit higher. So I'd probably vary this between 6 and 8, 6, 7, 8, 9, 10. Probably give it a little more granularity. Maybe go below 6 and see if that gives me any closer. Okay, so even more, there's more parameters. So now we're varying gamma, seeing what that gives us. So between 0 and, or I divided by 10, but for I between 0 and 5, or 0 to 4. So we're going to end up with gammas of 0.0, 0.0 to 0.4. And what are we getting? Are we getting any better? So we end up with the best value of gamma 0.3. So what they do after that is just run the values that we've got so far, see what we get. Accuracy of 0.98, and our training accuracy or area under the curve is 0.89. So see what they do a lot of comments here. Okay, so now they're moving on to tune other parameters, subsample and columns by tree. So between 0.6 and those are going between 0.6 and 0.9. And we have 16 different values. And we end up with the best one, 0.8 and 0.9. So here the 0.9 ends up being, or subsample 0.9 ends up being the best. So I'd probably go higher than that and try to see if 1.0 gives me a better one. Looks like, what do they do? Okay, they go closer in on subsample. So now I go 70 to 89, incrementing by 5, but divide by 100. So they're getting even closer between 7 and 7 and 9, 7.7 and 0.9. Actually, they're doing both of them that way. They're just getting more granular, see if they can get any closer. So here are the values they ended up testing. And did they get any higher? 0.841 before they got 0.841. So about the same. So they didn't really, well, they got a little bit. Okay, so now they're trying regularization. With regularization, turns out that if you do too much regularization, what they tried, 0.4 zeros and a 1, 0.01, 0.11, 100. For 100, ended up being pretty bad. So a 0.1 gave them a pretty good result. Okay, and then alpha is the other regularization. Alpha, they varied here. The best one they got was regularization of 0.01. Okay, then we step back, see what kind of accuracy we got. So this is the best, this is what they ended up having as the best value. 0.98 for accuracy. So 0.98 is where they ended for accuracy. Let's see what they started with. .9854 to start with for accuracy. And they ended up with the same accuracy, 0.9854. So they didn't gain much. Let's see, what about this? The 0.883645, let's see. That's they end up having a better AUC score when they started. So probably if we picked the best values as we went through, we'd end up actually improving when we got to the end. But because of either randomization or maybe the data changed between when they ran it and when I'm running it, it's a little bit different. So it ends up not necessarily being as accurate at the end as their first one. So as you can see, it's very, getting these to be as accurate as possible is just extremely tedious. A lot of, and you're not guaranteed of actually improving your model. Okay, so at this point, let's talk about homework. Basically, I have a lot of the homework, same homework as last week. Try these out on your own data set. The decision trees, random forest, XGBoost, like GBM, it's going to be a very similar process as what we just went through. Okay, and here's the here's the data that, or the code. This is for gradient boosting. So try this one out. Here's an example of gradient boosting using the models rather than our doing it by hand. And they go through parameter tuning just like we just went through, very, very similar, but for gradient boosting instead of XGBoost. So a couple other things is actually, the feature importance, make this so that each time you iterate, it is actually taking the best one. So that's what I'm trying to get at for these last couple. So it's been awesome sharing all this stuff with you guys. Kudos for those of you that stuck with it to the end. Basically, from here, I'm gonna take a break and possibly start back up after the holidays. And I'm thinking about, I've actually started putting it together, but creating a Udemy course on, with all of this material and more. There, the homework, will all be graded, and it's that's very exciting. I'd love to do that. And if you guys want to, get into that, just let me know. I can cut you a break on the price, because you've been through it once, but then going through that way, it's just a little bit different. More detail, of course. But let me know if you have any questions. Other than that, I appreciate your guys' attention, and it's been a great 9 weeks. This is fun stuff, and I hope you got a lot out of it. Definitely let me know how I did. Let me know if you if you do anything differently, if anything that we should add. Just get out there on Slack and let me know, either in the feedback or directly. But appreciate all you guys' time.